Questions? How many people were able to finish off the NIM attendance thing? Kind of, sort of. I wanted to finish that off here because 5.3 kind of relooks at the idea of induction and uses it to show you that formally this is when we had open definitions and closed definitions of sequences. You know, if you look at that, that's just recursion. And so if we look at parts of it, recursive formulas and inductive formulas and the rule of it. So 5.3 is really a continuation of induction. We still do induction, we do inductive proofs, and it begins something that we're actually going to get in the next section. We start talking about counting and advanced counting techniques. So there aren't any. So for NIM, we had the rule was we would take 1, 2, or 3. And we came up with the following definition, which was if you face n mod 4 equal to 1, you lose. On the other hand, if you face n mod 4 is the others, which would be 0, 2, or 3, you win. And we came up with kind of playing around. We played the game a few times until we saw a pattern going on. And we can use that pattern to help us understand what the proof is. And the pattern we had was obviously for n and the whole. If you face it, is it a win or a loss? If we had 1, you're going to lose. If you have a 2, what you did was take 1, and then you win. If you saw a 3, you would take 2, and you would win. If you saw a 4, you would take 3 and win. And we would notice that the modulus 2 mod 4 is 2, 3 mod 4 is 3, 4 mod 4 is 0. And so we would kind of continue this process. And so we would, if I would use that as my seed, as my building up the problem, and we would continue on with it, I would go through this and say, you know what? If I saw a mod 4 2, I'm probably going to take 1 always. If I saw a mod 4 3, I'm always going to take 2 always. And if I see a mod 4 0, I'm going to take 3 always. And that should put me into I win, the other person goes into a losing position. So if this is the idea behind it, if we want to go into the proof, we have our basis, which is obviously we have 1 stone. It's just pretty straightforward. 1 mod 4 is 1, and you lose. Or player 1 loses, really, if we would say it that way. So no big surprise. If you have 1 stone, you lose because you take it. And so it ends up being that the rule is followed, that if you see a mod 4 equaling 1, you're going to lose, we lose. So this is together obviously true. Then we go to the inductive. And we assume that the mod rule that we came up with works for n equal 1, n equal 2, all the way up to n equal k stones. So it doesn't matter. I'm going to have, if I take the modulus of 1, 2, 3, 4, all the way up to k, and I look what the result is, it's right. If it says I lose, I lose. If it says I win, I win. As long as I play by the way I'm supposed to play, right? Which is always put the other person into a losing position. If you do it, we're good. Now we have to show that mod rule works for k plus 1. All right. We just simply take the mod. We have these cases, so I'll take the losing case first. So 1. What if k plus 1 mod 4 is simply 1? I'm going to take the losing case first. Why is this a losing proposition for me? Well, what we have to do is say, how do you play, right? We can, part A, we could take 1. If I take 1 from both sides, what happens? We would have that k mod 4 is 0, right? So I face this. K mod 4 is what other player sees. I took 1 away from both sides, and so the other player is going to see k mod 4 because I took 1 away. Sorry, equals 0. All right. If the other player sees a 0, what do I know? Everything from 1 to k, the rule works. What does the rule say if you see a 0? If you face a n mod 4 and the answer is 0, you're a winner. So what is player 2 facing? This is a win for player 2. So player 1 equals lose. Is everybody okay with that? All right, let's say that would have been a bad choice, obviously. How about we take 2? If I take 2 away, k plus 1 becomes what? So it becomes k minus 1. And this would be congruent under 4 to negative 1, right? So what's the mod? Is everybody okay with that? But what does that see? That the rule applies because that's k minus 1. So therefore it's from 1 to k. So the rule is going to apply. So what do we know? What do we also have? Player 1 equals lose. All right. Well, player 1 could see. How about we take 3? But now I'm down to k minus 2, and that's going to be congruent under mod 4 to negative 2. But what does that mean? That means k minus 2 mod 4 is actually what? 2. Well, that's a win for player 2 again. So player 1 equals lose. All right, so true, right? The rule still works. If player 1 sees a 1, he loses. It doesn't matter what you do. Now, I could do this process for each. So the second one, well, what if k plus 1 mod 4 is a 0? Right? I could do this rule. What could I have done? I could go through here and do A, B, and C, right? I could do a take 1, take 2, take 3, right? And what would you find out is true? Well, let's go back up to here. What am I supposed to do normally? If you see a mod 4 gain 0, how did you do it? You took 3 to make yourself a win, right? What does that really mean here? If you take 1, you're going to put player 2 in a winning position, so you wouldn't do that. If you take 2, you put player 2 into a winning position, so you don't do that. If you take 3, you would put player 2 into a losing position. So I would do that. So normally when you would do the proof, if you have something like that, you would only do that one. You'd only write that. Because the other ones would lead to your loss. So how can you show that? Well, that's what? If I take 3, what is that? That is that k minus 2 is going to be congruent modulo 4 to -3, because I took 3 from both sides, right? So k minus 2 under mod 4 is equal to what? What's -3 the same as? 1, right? But what does that mean? Player 2 loses. So player 1 wins. All right, so it's, guess what? My rule still works. If you see a 0, you win. Sometimes it would be good to go ahead and do the take 1 and show that you would lose if you did it. And if you take 2, you would lose if you did it. But really all we're focusing on is there is a possibility for me to win. And so what do? You do the smart thing. Take 3 and you win. What would be the third thing? We would have k plus 1 mod 4 is equal to 2. If we go all the way back to our examples, if you have a 2, what would you do? For the 2, we took 1, right? So that means the 3 that you could check, right? A is we could take 1. B is we could take 2. C, we could take 3. Both of these lead to losses, so you wouldn't do it. You could show that, just like both of those led to losses, so you don't show that. But if I take 1, what happens? K mod 4 is simply 1. I just take 1 from both sides. And that is a player 2 loses. So player 1 equals a win. Therefore, does my rule still work? Yes, my rule still works. Fourth option is your k plus 1 mod 4 spits out a 3. I could A, take 1, I could B, I could take 2, I could C, I could take 3. Obviously the 1 and 3 will lead to losses, but to take 2, if I would take 2, I would have k minus 1 is what the player 2 faces. Mod 4 is 1, P2 loses. Therefore, P1 wins. True. So the entire rule works. We're done. Is everybody okay with that? You could go through here and on every single one of these do the whole, well, what if my answer is a 1? What happens if you take 1? What happens if you take 2? What happens if you take 3? Check. You lose them all. Then I'm facing a losing position. Well, what happens if k plus 1 mod 4 is a 0? If I take 1, I put him in a winning position, so I would lose. If I take 2, I would put him in a winning position, so I would lose. If I take 3, I put him in a losing position, so I would win, so I would take 3. In other words, this game theory is always about the idea of if the players actually play to win correctly, can you guarantee win-losses, right? So when we do the mathematics of game theory, when you do things of this nature, it's always under the assumption that they don't make a mistake. On the other hand, you hope that they do. And then you analyze the problem in a greater sense. Is everybody okay with that technique? Can you see how, I mean, this is just using induction, but do you see how this is actually useful? This is a game like NIM, and it's like, you know, why in the world do I have to do a strong inductive proof for a game of NIM? But do you see how this process can be applied to a lot of different stuff? On how you tear things down and test them appropriately and look to see what I'm supposed to actually do. And why does it actually work? It's one of those things that we always have to be asking ourselves over and over again. When you come up with, you know, mathematical modeling of the real world, we usually have to get issues like this. What are all the things that you could possibly do? My favorite, well, my favorite, but one of my examples for that would be my father-in-law who used to work in the test lab at AGCO, and they were going to have to pick between different battery manufacturers. And so they have all these different batteries, and it's like, well, we got a refrigerator truck. What would be a reasonable process to get this done and test them all at different temperatures of cranking amps, you know, and have the truck not have to go up and down, but only go up, because you have to respond differently at different temperatures, and then the test is going to have to do something else. And so it's like, well, it ended up being this kind of three-dimensional graph, you know, trying to go through. It's like, well, if this happens, you do this, and then, you know, you'd go through this entire process to get to what's a correct way of going to a valid conclusion. It's almost a sorting algorithm, but it was, instead of like a normal sort, like a tree sort, it was actually multidimensional, but same idea. And so the mathematics behind that's just simply the same. All right. For 5.3, what we do is begin something that we'll actually revisit later when we do advanced counting. And one of the things that we could see is in induction, we had this whole, you know, show for all n, p of n. So the first thing that we did was the basis case, which was p of the first element. Now put a little parenthesis here. It could be elements, right? Because the first thing might actually be a lot of things. It's like when we did strong induction for stamp problems, right? When you do things like that, if we would always say, you know, how much money can you form with $3 bills and $5 bills? Well, it's going to be $10 and more as you go in any amount. So obviously you have 3, you have 5, you have 6. You don't have 7, you do have 8, you do have 8 on, right, as you go through it. So really what you could do is just have 2 5s and a bunch of 3s. Why? Because 8 is a 5 and a 3, and then from that point on, just keep dropping 3s. And you would make not only 8, you would make 11 and 14 and every multiple of 3. 9 is 3 3s. Just keep dropping more 3s, and now you're going to make 9 and 12 and 15, every multiple, 10 as well, 2 5s. So as you're doing this, my basis element was the numbers 8, 9, and 10. Those 3 were my starting position to get going. And then I just start putting $3 bills down. So it might not be a thing, but kind of things make up the first element. Now, after you did that, you had your inductive case. And the idea of the inductive case, if we would look at this, is we would have that p of the first and p of the second and everything up to p of the kth implies p of the k plus first. Now I could use this idea and say that, you know what, for all n, p of n being true, this actually, the p of n could be a larger mathematical rule, like a function. I would say define a mathematical function. So we had functions in the past, and I'd say you could use arrow diagrams. You could use f of x equals so many, like x squared minus 3, all the different ways you can write functions. Well, one of the ways that we could write a function that would work for all the elements of the universe of discourse, all the elements is for all. For everything in the universe of discourse, you could make a function by starting off with the beginning. And what does this say? You start off with the start, your basis case, and then from here, what's happening is old values create new values. Really what you're looking at is the open form of functions. So in the past, I was using the word open functions for a sequence and closed form for a sequence when we did sequences of functions. It ends up that this open form is actually simply induction. And what was that? What did sequences? Well, that was chapter 2, right? Yeah, sequences in series, right? So in 2.4, for sequences, you had closed form. So example, say f of n is equal to 3 times 2 to the n equal to 0, 1, 2, etc. And then we also had an open form, which we said that the 0th element, I probably should use instead of f, might as well write that. F of 0 is equal to 3, but f of n plus 1 is simply 2 times f of n, where n is equal to 0, 1, and 2, etc. And so we had this open form and this closed form. The open forms themselves from this particular section ends up being, if we would look at this and say, well, wait a second. Hey, I could relabel this. This looks familiar. That would be the basis, and this would be the inductive component. So we've already done it. And so we're just going to change our terminology. So what we call the open form, we're just going to say, well, wait a second, this is induction. And since this is induction, we'll just go ahead and have, there's actually two different terminologies that we normally use for such things. And so our new terms that we talk about is A. These are what's called a recursive or an inductive definition of functions or sets. So not only can we build functions, we actually can build some sets out. And the first component here is obviously the basis. The basis is just simply define your first element or elements. Just tell me what you're starting off with. If it's a set, it's the number 3. What is it? That's my set. My set's going to contain the number 3. And so I at least say what my beginning elements are. The second thing that we do is the inductive or the recursive. So the inductive or the recursive rule is really what we're going to do is next value. The next value is equal to some sort of expression of older values or value. Classic example that we always do is the Fibonacci. Which would be this. F of 0 is 0, f of 1 is 1. We start off with our basis. And then from this point on, f of n, then we do our inductive or recursive. F of n is equal to, so my next value, f of n, is previous values. N minus 1 is the value 1 before, plus f of n minus 2, which is the value 2 before, and you always have to give what the basis of this thing is, which is equal to. So this starts at 2, 3, 4, etc. Always have to give the basis or this doesn't make sense, because you have to tell me, well, where does this thing kick off? All right, one of the things that you would do is you would, for inductive rules of this sort, normally when we talk about these recursive or inductive rules is what's called the degree of them. The degree of the inductive rule is What is the oldest element you need? This is kind of a rough definition. So if I would look at this, if to get to the nth, how far into the past do I need to go? 1 element, 2 elements, 3 elements, what? 2 elements. So that would tell me that this guy here is degree 2. Is everybody okay with that? One of the things that's important about the degree is if the degree is 2, that also tells you how many basis elements are necessary to kick it off. It's like, if I need 2 older things, how many elements are necessary to get this function working? Right? It's kind of like turning over an engine, right? What's necessary to get this turned over? You need to put some gas in, you need to, you have to prime it. Well, how do we prime this out? What's its degree? That's how many elements you're going to need to start off the entire process. If you do not have that number of elements, this thing won't start. And so note, degree also gives number of needed elements and bases. Obviously, we need to be able to run these sorts of things. So let's do some examples. Let's run it. Let's say that L sub 0 is 1, L sub 1 is equal to, say, -2, and L sub n is equal to L sub n minus 1 plus L sub n minus 2. And n is equal to 2, 3, 4, etc. These are called the Lucas number. A Lucas variant is the rule is Fibonacci, but we pick different starts. You pick any start you want, but you follow the Fibonacci rule. So we don't start with 0, 1, we start with whatever you want. And then the question is, what's the sequence that generates? All right, let's try it. Obviously, I start off with L sub 0 is 1, L sub 1 is -2. What's L sub 3? It's 2. L sub 2 is L sub 1 plus L sub 0, which happens to be 1 plus a -2. So what do I get? -1, right? What's L3? All we're doing is just adding the 2 numbers above. What's -2 plus -1? -3. What's L4? What's -1 plus -3? -4. What's L5? What's -3 plus -4? Everybody catch the pattern? All you're doing is adding the 2 above to get to the next. I don't care what changes on the Lucas is just simply pick different numbers in front and see what you get. If you look at things like this, now that you're looking at how many people have had differential equations? Do you start to see a pattern like new stuff from old stuff? Do you do that a lot in differential equations? And then if you have new stuff from old stuff, this idea of like, we have derivatives like second derivative and third derivative forms the original function type of work. And all of a sudden we have patterns generate. This will show up in the same way when we talk about separable differential equations, linear homogeneous, recurrent differential equations. Guess what? This will have the exact same sort of concepts as we do it. And eventually we'll get into recurrence relations like this, these inductive formulas. That will be things like, this will be linear homogeneous recurrence relations of degree k with constant coefficients. You kind of make your head, it's like, why? It's the same thing as diffie q. If you see this, do this. If you see that, do this. If you see this, do that. We're getting into a little bit more of a cookbook process. I'd like to see what my functions do. And so if they look like this, they'll have these answers. If they look like this, they'll have these answers. But for now, what we're left with is really just doing the functions, not trying to get some approaches to it. But eventually, we're going to revisit these and not just simply do it, but ask, are there different ways to write it? How do I go from an open form to a closed form when all I had normally was just substitution, right? Induction, you just plug it in and try to guess the pattern. If you can't guess the pattern, what do? How do you solve by guessing? I mean, it's valid, like in differential equations. What function added to its second derivative is always 0? Sine or cosine, right? And you guess it and you check it. Hey, if you had two solutions, what do? How do you put them together? And then we do things like the Wronskian and all these other sorts of things that combine different mathematics. We're going to do the same thing. We'll guess at answers, show the answers work, and then say, all right, how do we put those answers together? All right, but for now, we have these things. We can actually use, lots of different ones. But kind of more interesting is we could actually build sets. In the end, I actually did build a set, right? Functions are sets of ordered pairs. So I actually did build a set. I could actually write out the output and just simply write all those outputs. I was building sets. But we can actually do it a little bit differently. So for example, let's say that for my basis, I start off with the number 5 is an element of my set. Then my inductive component is that if x is an element of your set and y is an element of your set, then x plus y is an element of your set. So it's telling me how to take elements and put them together and still stay within my set. I could do that with other things, right? I could sit there and say start off with a basic object and then maybe union them together to stay within my set. It's really just simply if we would look at this and say, if these two objects are within this entire thing I'm talking about, when I combine them in this particular way, they stay within what I was talking about. So what happens here? Well, I start off with 5. So 5 is in my set. Well, 5's in your set and 5's in my set. What does that tell you? 5 plus 5 or 10 must also be in my set. So now what's in my set? Right, 10. And so just 10. So I just simply have, okay, so S is equal to 5 and 10. What if I did it again? 5 is in my set and 10 is now in my set. What does that tell me what's in my set? 15 is in my set. If I continue, what's my set made up of? So my set is all multiples of 5. So how did I generate all multiples of 5? Just start off with 5, and then say if you add an element in itself. How many people have had linear algebra? Does this look familiar? What's the whole idea of a basis set for a vector space? Why is it we called about, what's the idea of a vector space? The idea of a vector space was you simply say things like a scalar multiply vector addition, or whatever you call those things, stays in your set. The idea of I can get anywhere in my set if I want. So what is this process? Well, if I would do things like here in 3 space, right, where I take I take j, I take k, right? Any combination of I, j, k gets you where? Everywhere in R3. And so you had subspaces, you had vector spaces, but what are they? They are all this, an inductive definition of how to get everywhere based upon the basis and the rule to form it. So in linear algebra, what did you call your basis? Basis vectors. What was your rule? Scalar multiply them and add them, which really says what? stretch them, and add them together. So when we had things in linear algebra, and we had things like, oh, okay, and you would have things like, say, vector 1 and vector 2 are elements of your, let's call them the basis vectors, right? And then when we said things like span of v1 and v2 really was what? If I would stretch v1 and then stretch v2, which is really any vector in my set, right? For any, say, vi and vj, if we would call it that way, where vi, vj are in the basis, it's still in the set. So what's in my set? The basis vectors. What else is in my set? Any linear combination of them. Stretch them and add, it's still in my set. And then the question is, where do you all go? If you had 2 vectors that were linear independent, it formed a plane. If you had 3, it formed a volume. If you had 4, it formed a hypervolume. So all of that stuff in linear algebra is actually this. It's pretty straightforward. I mean, it's not that we just make it and we just change the terminology. But that's where the word basis came from. Spans. What's your entire set? Is it a vector space? Well, does the rules work? That's why we asked for closure, right? You tested all those things for closure, for a subspace. So is everybody okay with that? If you haven't had linear algebra, you're going to rerun this. But the nice thing is we can actually take all these sorts of things and just simply, it's just a building process. And this idea of the set, what all things you can get, when you think of it that way, linear algebra becomes a lot easier. When you say things like polynomial vector spaces or continuous functions, what are you really asking? What are all functions I can make given these 2 or 3 to start off? What are all continuous functions I can make given this? What are all places and vectors I can make given these starts? Here's my basic beginning. How do I put them together? Where do you all go? It's just this one section. Okay. Let's use these in proofs. So we're going to combine inductive proofs with functions that are recursively defined all together in one larger problem. Plus inductive proofs. So example, how about we prove that if I would take, note, if I ever write f sub n, I mean Fibonacci. That means f sub 0 is 0, f sub 1 is 1, f sub n is f sub n minus 1 plus f sub n minus 2, right? So knowing the Fibonacci numbers, I could prove that, let's say I take the first Fibonacci number and square it, take the second Fibonacci number and square it, take the third Fibonacci number and square it, and go up to the nth Fibonacci number and square it, and then add them all up. So I'm going to go through my Fibonacci numbers and square them and add them up to a particular point. It ends up being that this would have been the same as finding the nth Fibonacci number and the n plus first Fibonacci number and just multiplying it. Here'd be a fun one. Could you think of a physical, like a picture of this? Because f sub n and f sub n plus 1 has to be, it's a rectangle, right? Where one side is f sub n and the other side is f sub n plus 1. And this large rectangle is going to have to be what? A bunch of little squares on the inside. I have an f sub 1 squared, an f sub 2 squared, an f sub 3 squared, and all of this thing will form a big rectangle. That's what that's actually saying, geometrically. You can kind of play around with that if you want to draw a picture. Now, how do I prove that? If I'm going to prove this statement, okay, again, what do you know? I know that f sub 0 is 0, I know f sub 1 is 1, and I know that f sub n is equal to f sub n minus 1 plus f sub n minus 2 for n equal to 2, 3, and 4, right? Note, f sub n equals f sub n minus 1 plus f sub n minus 2 can be written in a lot of different ways. I could have written this as f sub n plus 1 is f sub n plus f sub n minus 1, where n is equal to 1, 2, etc., 3, etc. I could have written this as f sub n plus 2 is f sub n plus 1 plus f sub n, where n is equal to 0, 1, and 2, right? These are all the same. It's just how I want to write previous and last values by using a subnotation, right? They're all the same thing. Another way of looking at that would be this. The Fibonacci's, the f sub n, are 0, 1, 1, 2, 3, 5, 8. And I see this and I notice, what am I doing? I add. I add. I add, right? That means at any particular point in here, it doesn't matter where, if I had fk minus 2, fk minus 1, fk plus 1, fk plus 2, fk plus 3, I don't care how you write your values that are somewhere in the middle. What do I know? For example, those two add to that, right? So you could say things like, oh, look, I know that fk plus 1 is actually fk plus 2. Right? That's what that says. You actually, if you wanted to, you could write subtraction, right? Could I have fk plus 2 minus fk plus 1 is equal to what? Fk. Why? Because I can do algebra. It's the same thing. When you look at the recursive rules and you see this sequence, all of that exists. All of this. You have to understand algebra and you have to understand the process of how the function works. So when I say Fibonacci numbers, all of this comes along for the ride. In other words, you have to know how f sub n works. You have to know it. This isn't a straightforward, it always is written with the same index. That's not true. Two values that are right beside each other, added together, becomes the next value. It's the same thing as the figurate numbers. Two triangular numbers beside each other, added together, becomes a square number. The third triangular and the fourth triangular is the fourth square. Those are things that are just simply, you'd go through it and you would know those things. The same is true with these rules. Well, now that you know those things, how could we use that to do a proof? So here's my conjecture. f1 squared plus f2 squared plus everything up to fn squared is equal to fn plus 1. Proof. Basis. This is the basis case of the proof. What I want to do is what? Show P of the first element, right? That's what I want to do. Show that. What's my first element? The first Fibonacci number is f sub 0, right? But this isn't starting at f sub 0. What's my first element? F sub 1. We're picking n equal to 1. So P of n equal to 1. Okay, what does that denote? What's the left side? f1 squared. What's the right side? f1 and f2. What is f1? 1. What's f2? Let's go back up here. What's F1? 1. What's F2? 1. So is this true that 1 squared is equal to 1 times 1? True. Okay. Inductive. So the inductive case is, and we'll do strong induction, right? We are going to assume what? P of first and everything up to P of the... Do we only need... Let me look at this problem for a second. No, we can use weak induction. Normally you try kth, and which is what? What am I assuming? F1 squared plus F2 squared plus everything up to F k squared does indeed equal f of k plus 1. Right? We assume this. What's my goal? Show the k plus first. But what does that denote? F1 squared plus F2 squared plus everything up to what? F k plus 1 squared needs to be equal to k plus 1 and k plus 2. That's my goal. That's what I want to show. All right, your choice when you have equalities like that. Do you want to start off with the top equality, your inductive hypothesis, right? Do you want to start off with the inductive hypothesis equality and then just simply add things to both sides until it becomes the bottom equality? Or do you want to start with the left-hand expression of that, start replacing things with their equal until the right expression shows up? Do you want to do expressional work or you want to do equational work? Expression. Well, we had one equation, one expression. Let's have a vote. Equation, 1. Expression, 3. All right. So the expression version is start here until equal step 1, equal step 2, equal step 3, equal to that showed up, right? That's my hope. Start off with the left, step 1, step 2, step 3. Eventually the inductive hypothesis will be used, and then the right shows up. And then, oh, they must be equal. So we're going to try that technique. So, f1 squared plus f2 squared plus everything up to fk plus 1 is actually fk squared plus fk plus 1 squared, right? That is that. Is everybody okay? What is that equal to? Well, if I grouped this by the inductive hypothesis, let's replace it with what it's equal to. What is that equal to? What's that parenthesis equal to? Fk, Fk plus 1, and I still have my Fk plus 1 squared. Is everybody okay with that? Okay, where am I stuck? All right, this is where also step 1, step 2, step 3, know where you're going. What am I wanting to go to? That, which is a Fibonacci number times a Fibonacci number. What do I currently have? I have terms, and I have 2 of them. I need to get them to a single object. All right, so what do I notice in between those 2? What do they share? They have a common factor of fk plus 1, so we all know how to do algebra. Or maybe we don't, but I'm hoping you do. Fk plus 1 times what's left over? But
that is fk plus 2
by the Fibonacci rule, right? By the Fibonacci rule, are these 2 neighboring Fibonacci numbers? Yes. If you add 2 neighboring Fibonacci numbers, you always get the next. And so this is actually equal to f of k plus 1 times f of k plus 2. Because f of k plus 1 is simply f of k plus 2 is the Fibonacci rule. So we're done. So attendance, same idea as this last one. What we're going to do is, there's really not much definition, change from what I just wrote down. We're going to do page 358, number 18. What's different between this problem and what I showed? That problem is classic algebra, just normal algebra. 18 is linear algebra. We're multiplying matrices. So there's, instead of just normal algebra, it's linear algebra. Same concept otherwise. When you add and multiply, you're going to have linear algebra concepts. All right, that's it.